Okay. If I let this be, that's the 6x minus 11 over x minus 14. And if I switch the roles of x and y, I get x equals 6y minus 11 over y minus 14. Multiply both sides by y minus 14. And that gives me, so, do this over. That gives me xy minus 14x equals 6y minus 11. And I haven't gone through all the steps, but you really want to do that. Okay. Well, then I'm going to get my y's over on this side and my x's over on this side by subtracting 6y from both sides. And 6y minus 6y gives me 0. Now, I'm going to have xy minus 6y, and I'm going to write that out, xy minus 6y minus 14x equals negative 11. I'll write that again up here. Then I'll add 14x to both sides. And I'll note that we could have, I don't want to confuse the issue at this point, we could have added 14x to both sides at the same time we subtracted the 6y. And if you're used to doing that, it's perfectly valid. I'm doing it in 2 steps because I'm not in a hurry to get the answer. I want to make sure it's right. And I want to make sure I don't put too much stuff down here to confuse exactly what's going on. So I've got xy minus 6y minus 14x plus 14x equals negative 11 plus 14x. That's 14x to both sides. And now I have xy minus 6y equals negative 11 plus 14x. At this point, I factor out my y. And I get x minus 6 times y equals negative 11 plus 14x. Maybe the trickiest step here. It's one that people forget, miss a lot. I think I remember when I first did these, I missed that step once or twice. Okay. Then it kind of, you learn your lesson and you know what you're looking for. So now I divide both sides by x minus 6. We do it like this. And of course, this can be rearranged. Your numerator is x minus 6 times y times 1. Your denominator is x minus 6. You write x minus 6 over x minus 6 times y. So I'll do that. And I want to keep emphasizing. So we would have this. And x minus 6 over x minus 6 is 1. This gives us y. Little myself here, we get negative 11 plus 14x over x minus 6. I'm not going to do it now for interest of time, but we did it last time. And we check. And if I did all that right, it's gonna work out. So that's that problem. On this problem, we do a similar thing. We get let's say my A and B are 6 and 9. Get y equals 6 plus the square root of x minus 9. Inverse function, we switch x and y, we get x equals 6 plus the square root of y minus 9. And we solve for y. Well, we subtract 6 from both sides. I'm not going to write out details of that stuff. Then we square both sides. So we get x minus 6 squared equals y minus 9. So that y equals 9 plus the quantity x minus 6 squared. Now there's a problem with this. If we graph this function and this function, we can see what the problem is. It's not that this is wrong, but we have to restrict this domain a little bit. Because our root function is the inverse of your squaring function, but it only works for the positive part of that inverse. I don't want to go into the details of that right now. But the basic squaring function is going to have a graph that looks like this. Okay. Now the inverse of your squaring graph, you flip your x and y coordinates, you get something like this. In other words, your basic squaring graph gets flipped and transposed in a way that I'm not going to detail right now. But right here is your square root function. And if you invert the columns of your squaring function and graph what you get, you'll see that the points follow this curve. But we only use this part of the curve because this whole curve is not a function. That's past the vertical line test. If I give you a value of x, you're going to get 2 values for y. Okay? Points on this graph will include 4, 2, and 1, 1. Okay. Why do we include 4, 2? Because the graph of the squaring function has the point 2, 4. We switch those coordinates. Switch the coordinates 2, 4 of the basic squaring function. We get the point 4, 2 on the square root function. So there's what our graph looks like. But now we're going to do the square root of x minus 9. What's that do? That shifts the graph 9 units to the right. And now, this isn't really 9, let's pretend 9's all the way out here. It's not all the way. And we transform this graph, we shift it 9 units to the right. It'll have the point 13, 2 and 10, 1. And then we've got to do 6 plus the square root of x minus 1. Well, that's going to raise it off the end of the board, right? But now we can kind of draw a graph of what this thing should look like. Here's 9. And let's say that here is 6. So the 0.90 here is going to go up. Then we're going to vertically shift this graph 6 units. It's going to have this point. And then every point directly above this. Now here's 2, here's 1. So 10, 1, be like this point, and 13, 2 would be like out here. So the graph is going to look a little flatter on this scale. But here is kind of what our graph looks like. Should be more vertical at the beginning, but ballpark to take what we have there. Okay. Now, what's y equals 9 plus x minus 6 squared? So x minus 6 squared as its vertex is 0, 6, because you shift it 6 units to the right, and you lift it 9 units. Now 9 units puts it up here, or don't have a lot of room to graph. I should put this down a little bit lower. We'll go. Okay, so here's our graph of this function. So this graph is coming up and interfering with this graph. But, so here is our graph of G of x. And here's our graph of the inverse of x. Okay. Now, does it make sense that these coordinates are the reverse of these? Okay, well, this point is 6, 9, this point is 9, 6, right? I could draw other points on this. We have the point 7, 10. And here we have the point 10, 7. In other words, these points reflect across this y equals x line in a one-to-one fashion on this part of the curve. But this part of the curve has a tear dampers. Points that reflect off of this part of the curve are here. So this g of x function can't include these points because these points aren't getting reversed down here because they correspond to values that would give you a negative under your square root. Not going into detail on that materials, so to do that. But what this means is I have to eliminate this part of the g of x graph. The part of the g of x graph that corresponds to this curve or reflection is only the part for x greater than or equal to 6, part on this side. Part on this side isn't part of the function. Okay. If you, for example, took the point 5, 10, okay, which is on this graph, the 0.105 would not be on the graph of this function, because 10 minus 9 is 1, right? The square root of 1 is 1. That would be 0.107 if you plugged into this. So it just doesn't work. You have to then restrict both of these functions to domains where they're increasing, or where they're one-to-one. Okay. So that the inverse of this would be 1. You have to restrict this function so that you don't have two x values for the same y value. So that on this function, you won't have two y values for given x value. Now, for a number of reasons, you want to do that. It's kind of important. So that's the idea of inverse functions as it's approached in this chapter. Okay. I don't want to go too deep into that until I get a better look at your homework. Okay. I might talk about it a little more. What's an exponential function? First of all, in terms of our basic functions, an exponential function is a vertically stretched, horizontally compressed, and vertically shifted basic exponential function. Okay. The form of that is you here. That's 2 to the cx plus k. A times 2 to the cx plus k. Vertically stretched. The vertical stretch is by factor A. Horizontal compression is by factor C. And the vertical shift so that's in terms of our basic function. It means if we start with a basic exponential function, we stretch it out this way. we squeeze it in this way or squeeze it out, okay? Stretch it out this way. And we move it K units. We move it up or down depending whether K is positive or negative. Now, K equals 0. Then Y equals A times 2 to the C X. Okay, because K is 0, you don't have to write it down. And by the laws of exponents, that's A multiplied by 2 to the C raised to the X power, because if you do a power of a power, you multiply the powers. So A to the C to the X, A to the, or 2 to the C to the X is 2 to the CX. And that's AB to the X will be equals 2 to the C. So everything we're doing here connects back to the basic exponential function y equals 2 to the x, which is easy to graph. And the graph of every exponential function looks like the graph of a 2 to the x function. You just have different labels in the axes. Well, assuming now that the form a b to the x say the y equals ab to the x has a graph that passes through the points 2, 7, and 5, 12. So well, let's say here's 8, here's 4, and here's 2, and here's 1 and 3, and so forth. Okay, that mark wasn't very good. And let's say we got 16 up there. We've got 8 here, 4 here, 2 here, 1 here. Not particularly well scaled. A 2, 7 would be 2, 7. There's a point on our graph, and 5, 12 is a point on the graph. Now we can draw something that looks like an exponential curve through these points. It's not going to go through 0, 1 and give it a shape like this. It's got to have the shape of an exponential, so maybe that shape is something like this. That's reasonable. Not necessarily all that accurate, but it's reasonable. Because that pretty much has the same shape as a 2 to the x function, doesn't it? Okay. So right there's our function, at least some vague depiction of the thing, approximate depiction. Okay. We want to find A and B. How do we find A and B? We just write a couple of simultaneous equations to solve them. So y is 7 if x is 6. So if I plug 6 and 7 into this form up here, y a b to the x, what do I get? Replace y by 7, replace x by 6. Write out the equation you get. Let somebody questioning that. I have no idea why I wrote down 6. Your point is 2, 7, right? So y is 7 when x equals 2, not 6. And then, of course, you're going to have another one, y equals 12 when y equals 5, right? When x equals 5. So you get an equation for these two values. You just plug in the y and the x, you get an equation. And same thing here, you get another equation. And those equations are actually quite easy to solve once you see how. And then we've got both of them. Okay, so that's it. Most people got the first equation at least, and many people got both. Okay, so y equals 7 if x equals 2. Well, if we replace y by 7, y is a thing on the left of the equal sign, so we get 7 equals. X is up here the exponent on b, right? So we have 7 equals a b squared. And if you do the same thing down here, you're going to replace y by 12. You get the x, a b to the x, you're going to replace that by 5. Okay. Now, can you solve the first equation for a? You get a equals what? Well, here's the square root here, okay? But if you do the square root of one side, you have to square root of the other side. And well, you did the square root, you did the other thing, the square root, okay? So you would get the square root of there. Okay, you do the square root of both sides. It's not necessary to do that. If you got the square root of a equals this, you have to square it to get a, right? Which would give you 7 over b squared. Okay, but if you just divide those out by b squared, you get that much stuff.
Oh, okay, good point.
Okay, You didn't do the square root of A, and that's the thing that was wrong with your step. That's the only place you went wrong. Okay. Of course, if you'd have done it the easy way, that wouldn't have been a problem. But you don't really want to square root. You're trying to solve for A, so you really want to mess with that. Still, that would work. The little roundabout, but it's good out where it would work. Okay, now, actually, a majority of you. Okay. Apparently, I recorded through all those comments. Fortunately, I didn't insult anybody by name, so nobody knows who asked comment. Okay. But 60% of the class, I tried to use square roots to solve this for A. Okay. And if you remember the square root A as well as everything else, you would have gotten a good solution for the square root of A. Of course, you're trying to solve for A, and there's really no need to do a square root. Okay. So I'll just kind of jot that one down up here. If you divide both sides by B squared, you get A, right? And that's pretty much one step that you make two out of, right? So A is 7 over B squared. Now let's plug that expression in for A in the second equation. Like this into the second equation, what do you get? Let's go ahead and pause this one. Okay. People did quite well with that. You plug this into the second equation and you get 12 equals A, but now A is 7 over B squared times B to the fifth. Okay. Now notice what we've done. We started with two equations that both had two unknowns, A and B. You get down here, we have an equation that says one unknown, which is B, and it turns out it's really easy to solve for B. But we got to see the steps of the algebra. So let's come up here. We got 12 equals 7 over B squared times B to the fifth, right? Well, we can rewrite that. That's 7 over B squared times B to the fifth over 1. And we can write that as 7 over 1 times B to the fifth over B squared. Swap that up. And we end up with 12 equals 7 times B cubed. It's very simple algebra of fractional expression, okay? Now, you might have a habit that tells you, well, b to the fifth over b squared is b cubed. Make sure you check that habit out, but that would be correct. Okay, so how do we solve this for b cubed? How do we solve this for b? Well, I'm going to show you because we don't have too much time with this. Okay. So for b, we have 7 b cubed equals 12. We'll put b on the left because that's what we're used to doing. We're trying to isolate b, so we divide both sides by 7. So b cubed equals 12 sevenths. Okay, does anybody want to tell me, as soon as I pause this, how we solve b cubed equals 12 sevenths for b? Okay, people say do the cube root. Well, I'll do that, but I'll show you a different way that's easier to put into your calculator. Okay? Just putting a cube root in involves using the nth root thing and putting the numbers in right. You do either. So we can say the cube root of b cubed equals the cube root of 12 sevenths. So that b equals the cube root of 12 sevenths. But what's the cube root of 12 sevenths? Well, let's see, 12 sevenths is about 1.7. If I cube 1.2, I get 1.44 and get about 0.3. That's pretty close. 1.2. Put that into your calculator. Okay. Now, an alternative way get compared here. Take the 1/3 power of both sides, which is the same as the cube root. But you have to understand why that works. B cubed to the 1/3 is b to the 3 times 1/3. Okay, and of course that's 12 sevenths to the 1/3. So that b to the 1 equals 12 sevenths to the 1/3, which is the cube root. It's about 1.2. That's a matter of preference, how you really want to put this into your calculator. But you should be able to do it either way, so you have the option. Sometimes it's a lot easier to deal with fractional exponents than it is radicals, okay? I always found it much easier, but different people, you know, everybody's brain works a little bit differently. Most work better than mine, but everybody's brain works a little differently, so some people prefer one way to the other. But you make sure you're secure in the way you do this. Okay, I think I recorded all this, but just to be sure b cubed is 12 sevenths. Do the 1/3 power both sides. We get 3 times 1/3 for the power of b, which is the first power, which is just b. And we get 12 sevenths for the 1/3. And as I said, some people find this easier to put into their calculator than the radical expression, cube root of 12 sevenths. That's your choice. Okay, so anyhow, we find that b is approximately 1.2. If that's right, what is the value of that? Okay, so yeah, just what is it that we see over here that allows us to find a if we know b? Well, some people kind of pointed, I think they're pointed here. We solved for A in terms of B. A is 7 over B squared. So now that we know B is 1.2, it's really easy to find A, doesn't it? Okay, so go ahead and do that. Okay, as I just said, people are messing up a few details, but have the right stuff, okay? But you got the devil's in the details, so you gotta be careful about the details. Okay, to find A, well, as we see here, we solved, the first thing we did was we solved the first equation for A, which gave us A in terms of B. So we just say that, okay, A equals 7 over B squared. That's 7 over 1.2 squared, which is 7 over 1.44, which is very close to 5, just a little less than 5. Probably rounds off to 4.8 or 4.9. Okay. So there we have it. So now approximate function y equals 5 times 1.2 to the x. Now remember, we can relate that to the basic 2 to the x function, but we're not going to do that right now. That gets a little more complicated. But 2 to the c would equal 1.2. We solved that for c using logarithms. We haven't gotten there yet. Now, if you're in the MDE 61, you have, and you would know how to do this. But we're not going to pose that question right now. We're just going to observe that this can be connected to our basic exponential function in a way that makes it clear why this graph looks just like the graph of the basic exponential function, just with different numbers on the axis. Okay. Now, let's see what good this is. Well, I do recommend, and it'll be posted, that you take a look at the MDE 61 for this date, okay? Because it works out a lot of stuff in great detail. But maybe you don't need the detail. Maybe your book is going to tell you everything you need, okay? Maybe the materials and the examples you see. But I recommend that too. We go pretty slowly through the whole process. If you need a slow introduction to the process, there it is. Okay, anything. Okay, so let's say we got we have a tank with 100 guppies. Every week the population increases by 10%. So here we have a table. Week 0. The population is 100. The increase is 10% of 100, which is 10. So the end of week population is 100 plus 10 equals 110. Everybody understand that? I assume everybody does. If you don't, look back at the MDE 61. It'll be posted sometime later today. Okay, so in week 1, here. Beginning of the week population is now 110. Your increase is 10% of 110, which is 11. Okay, so that's 110 plus 11 equals 121. Now we're going to get a fractional guppy in the next week. So in week 2, our population is 121. 10% of 121 equals 12.1. Now we can interpret that as 12 with a 10% probability of another one. Okay. So we write that as 121 plus 12.1 is 133.1. Again, 133 with a 10% chance that there's 134. Okay. The third week, we've got 133.1 guppies. We add 10% of that. Now we've got a 31% chance of an extra guppy. And we have 146.41. Okay. Now, there's a quicker way to calculate this. Okay. Adding 10% they're obviously, it's a history class, they're obviously studying the 60s. You just walk in there. One look and they understand they don't want to know anything about the 60s. Oh, well, anyhow. Well, that's the music that was playing when I was your age. Okay, actually a little younger than you. Yeah, 2 years younger. Right? No, actually about the same age. Yeah, okay. Yeah, go back 730 years. And that's what the music sounded like. And I've got to lock the door because when I hear that music, I just got to start dancing. And if I start dancing, you'll never want to look at dancing again in your life. It'll ruin the whole aspect of your existence. So we're going to lock the music. Okay. Good music. Adding 10%, at least I like it. Adding 10% back to this is the same as multiplying by 1 plus 0.10. Because if you multiply 100 by 1 plus 0.10, you multiply 100 by 1 and it gives you what? 100, right? Then you multiply 100 by 0.10 and it gives you 10. So it's 100 plus 10, 110. And that's exactly what we did here, okay? And that applies everywhere. If we multiply 110 by 1 plus 0.10, we're multiplying 110 by 1, which gives us 110. And 110 by 0.10, which gives us 11. And then those are added. But 1.1, 1 plus 0.10 is 1.10. So now the fact that you're adding your 100 to your 10% of 100 or whatever It's kind of disguised, but not that badly disguised, okay? You can still see it. You're gonna add 1 times that number plus 0.10 times that number. So when we do this, we could also write this as correctly 1.10 times 100 equals 110. And here, instead of doing this step, we don't have to calculate the interest or the number of new buildings, okay? This would be 1.10 times 110, which is 121. This would be 1.10 times 121 equals 133.1. Okay. There's still another way to write it. Okay. Where'd this 110 come from? That was 1.10 times 100, right? So we multiply 1.10 times 110. We're multiplying 1.10 times 1.10 times 100, right? What's another way to write 1.10 times 1.10? 1.10 squared. This then would be well, it's 1.10 times 121, which was 1.10 squared times 100. So we're going to have what? 1.10 cubed times 100, right? Every week we multiply by 1.10. So now, these numbers here are 1.10 times 100, 1.10 squared times 100, 1.10 cubed times 100. Number of the week matches the exponent of your 1.10. And there's a good reason for that. Again, every week we multiply by another 1.10, which raises the power by 1. So that, let's see if you're following this. How much do we have after 8 weeks? We really don't have to do any of this once we see the pattern. Can you write out what we would have after 8 weeks? Just a calculation. You don't have to plug it into your calculator, although you usually can. After 8 weeks, we're going to have 1.10 to the 8th. Okay. And again, there are 2 reasons for that. One is that's the pattern. Every time we multiply by 1.10 to get the new number, we're going to add 1 to the number of 1.10s we multiplied by, which will give us 1 more power. So there's the pattern, and you can kind of prove the pattern. That's kind of related to what we call mathematical deduction, but we're not going to get into that, unfortunately. So we have this. So what would you have after t weeks? Well, t is the number of times you multiply by 1.10. Every week You increase the population by 10%, you multiply by 1.10. Okay. So our population function is, I'll say P of T equals 100 times 1.10 to the 2. Means after 2 weeks, we will have multiplied by 1.10 T times, which means we multiplied by 1.10 to the 2. It's really, once you understand it, and you really want to try to understand this, as we saw in the support class last period, this also applies to finance. If you have 10% interest compounded every year, then this is how much you would have after 2 years if you invested $100. The curve is just the exponential curve. And you can draw that curve like so. What will the coordinates of this point be? Well, this point occurs for t equals 0. This is t. And this is p of t. This is the point 0, 100. Okay. Now, if you calculated the 8th year, you would get something like $220 ballpark. You plug 8 into this expression, I think you get something pretty close to 220. So if that's 100, this would be 200. And 220 would be about here. So you have the point where t is 8 and y is 220. So now you could predict what you would have after 20 years if you had an accurate exponential function. Okay. Notice that in 8 years, you've a little more than doubled. This would double in about 7 years. And you could solve for that using logarithms, which we'll get to next week sometime. Okay. This is an exponential function. For A equal 100, B equal 1.10. So a little bit of terminology. The value of B is your growth factor. And it's 1 plus the growth rate. So the growth rate is your 10%, which is the same as 0.10. I'm assuming that you understand percents well enough to understand what's going on here. Okay. We talked about that some in the MDE course, but percent means per 100, 10% means 10 per 100, which is 10 over 100, which is 0.10. Okay. And if you don't understand that about percent, it's probably because people put a calculator in your hand, let you use the percent button instead of thinking. So you need to get over that because you need to write these things out, okay? But I think you'll be okay with that. All right. So hopefully that'll give you some preparation for the assignment, which is a combination of using these functions and interpreting them and plugging in the 2 points and finding what the function is. Okay. One last thing. If we took these 2 points and did what we did before, you know, your y a b to the t form, and plug the x and y for this point and the x and y for this point, we would come out with something pretty close to a equals 100 and b equals 1.1. Okay. We'd come out with exactly the same thing because the 220 doesn't exactly match this function, but it's probably to the nearest 10, probably accurate.